All right, Eduqas A-Level Component 2 from 2022. I'm going to take you through this question by question and try and explain as clearly as I can the process in each of these questions. So I'll probably go a little bit slower than if I were just doing the paper, and the total may take a little bit more than 2 hours, but I will try my best to make the rationale clear as I go. So question 1, point P here represents a junction in an electric circuit where 5 current carrying conductors are joined. Part I is asking me to determine the value of I and indicate its direction on the diagram. So here is I. So I'm basically working out how much current needs to flow in this branch. This is a test of Kirchhoff's first law, which says total current into a point must equal total current out. Basically conservation of charge. The current has nowhere else to go, so the total that flows into any point must equal the total out. So let's have a look at P. How much current have we got going in? We've got 1.2, 0.4 and 0.6, total of 2.2. Coming out, we've got 0.8, which is clearly less. Therefore I must make up the difference. So that is basically what we're saying. So 2.2 equals 0.8 plus I. Therefore, I must be equal to the difference between these two. So 1.4 amps. And that needs to be coming out from P, away from P. Calculate the number of electrons passing point Q in 1 second. So here's point Q. It has a current of 0.8 amps. Flowing through it, so 0.8 amps is equal to 0.8 coulombs per second. So 0.8 coulombs every second. So if I want to know how many electrons that represents, I can simply divide by the charge on one electron. I'm just gonna, it feels like I should be able to do that in my head, but I'm going to double check it on the calculator. Why take chances? 5 times 10 to the 18. Electrons per second. Okay. So Charlotte's investigating circuits involving combinations of buzzers in the circuit below. P, Q, S and T can be controlled using switches X and Y. The buzzers are identical and their resistances remain constant. So this is a slightly unusual circuit in that the switches are in parallel. So what that means is if we were to close X, that would give the current a zero resistance path to follow. So the current would completely bypass S. Closing X therefore effectively takes S out of the circuit. And similarly, Y will do the same thing for buzzer T. So initially X and Y are open, and in this arrangement all 4 buzzers are on. With X and Y open as shown, ammeter reads 18.2 milliamps. Calculate the resistance of each buzzer. Okay, so the total circuit resistance, this is a parallel circuit, so calculating total resistance in parallel, we do 1 over total resistance is going to be equal to 1 over the resistance of the top branch, which is 2 times R, because there are 2 buzzers in series, plus 1 over the resistance of the bottom branch, which is also 2 times R. So 1 over 2 times R, 1 over 2R plus 1 over 2R equals 2 over 2R. Which just equals 1 over R. So the total resistance is just equal to the resistance of 1 buzzer. And then I can just apply Ohm's law, V equals IR, and say that since V equals I times R, R by definition is the ratio of V to I, equals 6 volts. Oops. Divided by, what did it say the current was? 18.2 milliamps, so times 10 to the minus 3. Chuck that in the calculator. 329.7. And in general, I wouldn't give an answer to 4 significant figures, so I'll round that to roughly 330 ohms. There are alternatives for ending up at that same number. You could look at this circuit and you could say, well, if that is 18.2 milliamps, the 2 parallel branches are exactly the same, they're identical, so that current will split to give me 9.1 milliamps on the bottom. These are in parallel, so each branch has 6 volts across it. Therefore, and since the buzzers are identical, I could say that there are 3 volts across Q, and I could just apply Ohm's law to 3 volts and 9.1 milliamps to get the same result. Whichever, it doesn't really matter, whichever method makes the most sense to you. Okay, Charlotte predicts that the ammeter reading increases when X is closed and increases further when X and Y are closed. Determine whether she is correct. Normally when you see determine, that basically means apply some physics, do a calculation to conclude whether or not she is correct. So determine. So let's do the calculations. For X closed, if X is closed, let's have a look at our circuit. If we close X, the resistance of this top branch S is taken out of the circuit essentially. So by closing X, the resistance of this top branch just becomes 330 ohms because there's only a single buzzer, while the branch below it would still have a resistance of 660 ohms. So the total resistance of the circuit would be equal to 1 over 330 plus 1 over 2 times 330. Okay, and then always remember we will have to turn that back upside down again to get the total resistance. I'm just putting this into the calculator. So the total resistance is 220, and by Ohm's law, current is equal to V over R, 6 over 220, gives 27.3 milliamps. 27.3 times 10 to the minus 3. So far so good. With X and Y closed, if we go back to our circuit, if we close Y as well, we get rid of buzzer T. That means the resistance of this lower branch becomes 330 as well, because it only has a single buzzer in it. So with X and Y closed, 1 over that total resistance equals 1 over 330 plus 1 over 330. Oh my goodness, not sure what happened there. I think the computer's trying to turn my writing into a ship to help me. So that's 2 over 230, which implies that the total resistance is half of 330, which is 165 ohms. Therefore, current 6 over 165 is 36.4 milliamps. So Charlotte is correct. The initial current at 18.2 has increased when X is closed and has increased further when X and Y are closed. Part 3, final part. Charlotte uses a decibel meter to measure the loudness of the sound emitted by the buzzers. She records that the sound is twice as loud when only 2 buzzers are operating compared to when all 4. By determining power, show that these measurements are to be expected. So power is V times I. So for 4 buzzers, that's our initial setup, the 4 buzzer setup with both switches open. And we were told that this current was 18.2 milliamps. So for 4 buzzers, milliamps. Total power then 6 times 18.2 times 10 to the minus 3 gives 0.11 watts. For 2 buzzers, VI 6 times, and we can use our answer from the previous question, 36.4 times 10 to the minus 3. We can see already that that is indeed double the current, so it is going to give double the power, 0.22 watts. So this is a 3-mark question, and I would suggest we've got ourselves the first 2 marks. Show that Charlotte's measurements are to be expected. What's that 3rd mark going to be for? I would suggest we need to make some statement to say that double the power implies double the loudness. 2 buzzers, double power of 4 implies double loudness. We might not need that statement to get the full marks, but why take any chances? We know that that's true. Job done.